Hey guys, welcome back to Food for Thought Physics, where today we're going to be analyzing the kinematics of uniform circular motion. Uniform circular motion has two main properties we need to be aware of. One, it has to do with an object moving in a circular path. It's going to be moving in a circle as shown here. This is kind of implied by the fact that it has circular in its name. And two, the object must be moving with constant speed. And this constant speed is why we call this a uniform circular motion. The uniform just means the speed is going to be uniform or unchanging. Now, usually when we look at kinematics, we deal with position, velocity, and acceleration. Here, the position and velocity are not of much interest to us, so we'll mainly be focusing on the acceleration of this object. Now, you might be wondering, how can an object moving with constant speed have any acceleration? Well, remember, acceleration has to do with the rate of change of velocity, not speed. Velocity is a vector quantity, which means that it has a direction as well as a magnitude. And well, you can think, well, if an object's moving in a circle, the direction of the velocity, should be changing a lot. And due to this change in direction, there is an acceleration. So now let's look at what this acceleration might be. The important thing to note is that at any given point on the circle, the object is going to be having a velocity vector that is tangent to the circle at that point. So let's draw a velocity here. We're going to label this as v naught. So our initial velocity is here. And let's say that an infinitely small amount of time has passed, some tiny dt. Well, after a dt, let's say, for instance, that the new velocity looks like this. Or let me draw that a little better. Let's say that the new velocity looks like this. It's going to be the same length, it's constant speed, so the magnitude is not going to change, but the direction, as we see, has shifted a little bit. We're going to call this new velocity v1. And let's draw these radii to the center of the circle here. And we're actually going to label this radius as being r. So now, in this infinitely small change in time, this dt, you can imagine that the object has moved through an infinitely small angle. This angle here, which we're going to call d theta, an infinitely small theta, the differential element. And you can also imagine, well, the object has moved through this small length, this infinitely small length. So we're going to label this length here as dl, a differential length L. So now, a very important thing to notice, which we'll use later, is that this dl is actually going to be a straight line, not an arc. And the reason that this is, again, kind of intuitive, if you can imagine zooming in on an arc, if you take a very small slice of an arc and zoom in, it'll be very near straight. So you can imagine, since this dl we can think of as infinitely small, then it should be actually exactly straight. So we can imagine this as exactly straight, or at least an approximation. The approximation actually gets closer and closer to perfectly straight as we shrink this d theta to infinitely small. So now, continuing on, let's first draw these velocity vectors over here to get a better idea of what they look like. So we're going to have a v0 here, and it's going to change into this v1 over here. So, well, from v0 to v1, you can imagine in this infinitely small period of time, what has happened? Well, the velocity has changed from here to here. And we're going to call this infinitely small change in velocity in black. We're going to call this dv, this infinitely small change in velocity in an infinitely small period of time. What else do we notice about this triangle? Well, this angle here should be d theta. You can kind of see why that it should be the same as this angle over here. So this is going to be d theta. And since d theta is infinitely small, and these two angles should be the same, as this is an isosceles triangle, since d theta is infinitely small, we can think of it as 0, or rather as infinitely close to 0. So these two angles are going to be right, or at least infinitely close to right. So this doesn't really make sense, but when dealing with these infinitely small values, these infinitesimal values, we get some strange things like this. So, well, since these angles are both right, well, what does that mean? Well, that means that, first of all, this dv, we know, this change in velocity is going to be the same direction as the acceleration. So if the change in velocity is perpendicular to this velocity vector, which we know is tangent to the circle, that means that the change in velocity, and therefore the acceleration as well, must be perpendicular to the circle. So it's going to look like this. It's going to actually point towards the center of the circle here. So the A is going to be pointing in this direction. Over here, it's going to be pointing in, say, this direction. It's always going to be pointing towards the center of the circle. We call this a centripetal acceleration. And this is a fancy word, so I'm going to write that here. A centripetal acceleration. The centripetal has this centra, which means center, and this pedal, which means pointing. So centripetal acceleration is the same as center pointing acceleration in Latin. So this is why this acceleration is going to always point towards the center of the circle in uniform circular motion. So now that we know the direction of the acceleration, let's figure out the actual magnitude of the acceleration. Well, here we can use these triangles, which we know have the same angles here, so that means that they're going to be similar triangles. Using similar triangles, we can set up a proportion. Over here, we're going to have that dv over v. Now notice I use this v and not a v0 or a v1, because since we're only dealing with magnitudes here, and we know that this constant speed implies that the magnitudes of both these vectors are the same, then we're going to have this dv over v here. Actually, I'm going to add some vector hats here. That was actually not very good of me. I'm going to add those vector hats just to make it more clear that these are all vector quantities. Now anyways, so here we see this magnitude of these two vectors should be the same, and we're going to just call it magnitude v for now. So we have dv over v is going to equal, we can look at a similar triangle here, it looks like it's going to equal dl over r by similar triangles, dl over r. So now we're going to move this dv over here and get that dv equals v times dl over r. Now remember, what we want is acceleration. So how do we convert this dv into acceleration? Well, remember, we have that a equals dv over dt. So let's just divide this entire equation by this infinitely small change in time, dt. That gives us dv over dt equals, I'm going to rearrange this side slightly actually. I'm going to write this as equaling v over r times dl over dt. So we're going to divide this term by dt and move this r over here. We'll see why that is in just a second. So what does this equal? Well, since we know first of all, this side here we see equals acceleration. The a equals dv over dt, as we learned before. And this dl over dt, well, this change in length over change in time, that's just going to be the velocity again. So we're going to substitute v for this term over here, and we get that the acceleration of this object, which is going to be towards the center of the circle, has magnitude of v squared over r.